Hi there, I just picked up this Advanced Instruments J3 signal generator from eBay, and this is its first test. The scope is plugged into the sine wave low impedance output that can do 3 volts, and not much is happening when I power it on. Well, something is happening on the meter and scope. There are massive oscillations, and then it settles to normal levels. Actually, the manual warns that this happens and recommends to start with nothing connected or the output controls all the way down. Nothing wrong with the sine wave. Frequency changes when I turn the large frequency knob. And the amplitude changes with the level control for the sine wave output. The other output is supposed to produce a square wave. There is something there on the scope. Unlike the sine wave level control, the one for square wave is quite noisy. Probably it hasn't been used for a long time. This is a positive square wave, so I need to change the scope's slope trigger point upwards from 0 volts to get a stable picture. There, nice square wave. Moving on to the balanced 600 ohm output on the left. First, center tap to one of the outputs. There's a massive signal there. Before using both taps for a balanced output, it's best to reduce the level a bit, because now the signal has twice the amplitude, going from 1 kHz to 100 Hz, and it's interesting how the control loop for the amplitude takes a few moments before it settles. Going from 10 kHz down to 1 kHz doesn't show that behavior. I found only 2 obvious issues with this J3 signal generator. The power on light doesn't work, and the indicator for the frequency dial is missing. For completeness, there are actually additional sockets on the rear. There's one pair on the right, which is another sine wave output, but this one is low distortion and has 5K impedance. The other pair of sockets is on the left as an input to run the generator on 40 to 48 volts DC, for example from batteries. Before diving in further, it may be useful to have a quick look at the specs and block diagram. To start with, my unit is the J3, not the slightly improved J3B, for which many more sources for the manuals are out there. There are differences in the schematic, so getting the right manual matters. The only J3 manual I found has some handwritten annotations from a user based, of course, on his or her J3, which may or may not apply to other J3s. Anyway, the frequency range goes from 10 Hz to 100 kHz. Above 100 Hz, the front outputs have a distortion of less than 0.1%, typically better than 0.05% from 200 Hz onwards. The rear output is better than 0.02%. The balanced main output can produce up to 30 volts RMS into a high Z load, which is quite a lot. With 600 ohm load, that reduces, of course, by half. While this is going on, the low impedance output can drive 1 watt into 5 ohms, to which the handwritten notes added typically. The other handwritten notes that all outputs were flat within 1 dB over the whole frequency range, and that below 50 Hz with load, the balanced and low impedance output could not supply the full voltage. Obviously, I'm going to check both of these statements on mine. The block diagram is quite useful to get an overall idea of the J3's design. This also applies to the J3B because the differences are only very minor. There is the actual oscillator using a Wien bridge circuit, which is a good choice for getting a very low distortion sine wave. That oscillator signal goes via the level control directly to a low distortion output at the back and is then fed to a power amplifier. The output of the amplifier is fed into a transformer which produces the low Z output as well as the balanced outputs. The sine signal from the oscillator also goes directly to a circuit called squarer, which forms it into a square wave which has its own level control and output. The power supply is interesting in that it monitors the power draw of the amplifier and will protect it from getting overloaded from whatever is connected to the outputs. If that should happen, the power supply will shut down the oscillator. Since the power amp is connected via a capacitor that conducts only AC, to the output transformer, shutting down the oscillations automatically disconnects the amplifier from the output. After a while, the oscillations will start again, and if the overload still exists, the shutdown will happen again, and so on. One last point. It's possible to feed an external signal into the low distortion output, which will be mixed with the oscillator signal, and the result is going through the amplifier to the low Z and balanced outputs. This feature may be useful for special applications. Anyway, enough theory, let's have a look how the J3 is put together. To open the generator, the top and bottom shells can be removed by turning the latches into positions where they no longer engage with the front and back panels. The reason for the surprisingly heavy weight of this generator is very obvious. It is built with lots of metal, and there are no less than 3 good-sized transformers in there. The output transformer in the block diagram is actually split into 2 mounted on top of each other. A large PCB on the rear, big electrolytic caps, and a transformer number 3, which is part of the power supply. Another view of the inside, not a single integrated chip, all discrete transistors. The big metal can in the middle contains the actual oscillator circuit. I put the unit on the side because that takes less space and still allows good access for probing components, concentrating mainly on all the electrolytic capacitors. They tested all okay, including this one, but the label on this cap states 470 microfarad and it measures nearly 610. An overachiever is always suspicious, as it usually means the capacitor is leaky. Most multimeters measure capacitors by timing how long it takes to charge or discharge, like here measuring the same capacitor with the Bryman 869S out of circuit. As leaky capacitors take longer to charge, they can confuse multimeters to show a much larger capacitance than they really have. In this instance, this is not the case. This capacitor reads high regardless whether DC charge-discharge cycles or AC at various frequencies are used. Neither is the leakage current excessive. Just in case, I replaced it with a new cap that measures close to 470 microfarad. And speaking of replacing, I consider what to do with a non-working power indicator. I checked that the voltage is present, which means the lamp itself is dead. That the failed lamp is in fact a neon light is in itself a bit of a mystery. The attached resistor, R11, color coding means it's 68K and its measures about 70K. The schematic shows that the neon and its resistor is wired in parallel with the 117 volt winding of the power transformer. The parts list shows R11 as having 47K. That would drive the neon at just 0.6 milliamp, which is already very moderate and makes it not terribly bright. But with the 68K resistor, this drops further to just below 0.4 milliamps. In either case, such low currents means the neon should last in the order of 50,000 hours or more. This is more than 5.5 years if the machine was on permanently. It is quite possible that in a commercial lab, equipment may simply be left running permanently to avoid having to wait for any warm-up periods. In any case, it looks as if the neon, and likely the whole generator, has clogged up a lot of runtime. Regarding the difference in resistor values, that is likely a change that was not updated in the J3 and J3B parts lists. I found quite some other errors that seem to have never been corrected in either version. I found that the lamp socket and the red cover fits a 3mm LED nicely, so that's what I've chosen to do. I considered driving it from 117 volts AC, but that would need at least one additional high voltage diode to protect the LED that can't handle such reverse voltages and a beefy resistor burning away the excess voltage. Instead, I choose to drive it from the DC of the smoothing cap, running the wire in parallel with the mains cable to the rear corner where the mains transformer lives, and then diving down to the smoothing cap. The heat shrink on the positive wire hides the 10K resistor that limits the LED current to a little over 4 milliamps. Running it from this cap has the advantage that the power light works regardless whether the generator is running from mains or external DC. The disadvantage is that it will fade slowly when the power is turned off, but then, if that fades fast, it's a warning that either the smoothing cap is turning bad or something draws excessive power. With nothing else really wrong, I decided to follow the maintenance manual in going about setting up the generator, which means you have to remove the rear panel to have access to the underside of the PCB. I want to highlight the solder joints of the two big caps on this PCB. Not wires, but actually quite substantial tabs, and they are folded down and soldered. Replacing those caps eventually is going to be fun. The reason why I need access to the PCB now is that it has holes to access the 4 trim ports. I marked them here. Owners of the J3B will notice they have one additional trim port. In fact, I was actually happily using the PDF copy of the J3B manual, which had a much better scan quality than the one for the J3, and only after I hunted in vain for said trim port I realized that the maintenance instructions, schematics and PCBs of the J3 and J3B are slightly different. Regardless of the version, both instructions have the same contradictions. For example, here I am following the manual to set up the power supply to 37 volts plus minus 0.5 volts by probing a test point that is labeled on the PCB as 36 volts. So I compromised and set it to not quite 37 volts. In another step, you should check that this point should be within 1 volt of half the supply voltage. 2 times 18.5 is 37, and just to check, the supply is still a tad under 37, but I'm definitely within a volt, so all's good. To set up the quiescent current in the power amp, this link needs to be opened. From the solder spots stuck on the cap nearby, someone definitely did this before, and quite carelessly, if I may say so. Anyway, the solder is stuck, melted into the plastic, and I can't remove it. The cap itself sits on some kind of cushion that looked as if it had started to disintegrate a bit, but on closer inspection it's fine, and the same is true for the cap, which tests okay. Not only does the link need to be cut, you have to solder a capacitor between 0.5 and 1 microfarad across. I used the 1 microfarad cap. Then you have to measure the DC current over the link. At least the added cap makes for good hookup points. Powering on, and after some time the current settles to around 12.5 milliamps. The J3B manual then tells you to adjust the current to 15 to 16 milliamps using trim port R129, which does not exist on the J3. The same section in the J3 manual says to adjust it to 18 plus or minus 2 milliamps by selecting a resistor and soldering it in. There is one already there, of course. The J3 manual also says that the voltage across that resistor should be about 1.2 volts. Since it is, kind of, and everything seems to work anyway, I decided to call it good enough and restored the link. I moved on to adjust the duty cycle of the square wave to 50%, which was done easily enough. Next, I had a look at the rise and fall times of the square wave. The spec says it should be better than 1 microsecond. Well, the fall time certainly is, with roughly 480 nanoseconds, but there is some funny stuff going on the rising edge. It seems there are 2 attempts in getting going, and only on the 3rd does the level finally stay up. By the way, the level at just over 6 volts is also too high. It should be 5 volts. According to the manual, problems with rise and fall times points to R135 and C133. Looking up C133 in both the J3 and J3B parts list reveals an astonishing 33 microfarad 500 volt specification. Really? Well, here is C133. You may be able to make out the legend C133 printed on the PCB, and of course it's 30 picofarad, not 30 microfarad, an error of just 1 million times too large. I don't have a 30 picofarad 500 volt cap, so I park any replacement of C133 for the moment and look at fixing the level problem first. According to the manual, a square wave with too high amplitude is tamed by adding a shunt resistor across 2 pins of the PCB. I set this up by adding a resistor decade starting at 20K. Successively dialing in smaller and smaller resistors and observing the amplitude of the square wave, I managed to get it close enough to 5 volts. And the needed shunt resistor is 3.3K, which happens to be a standard value. And here it is, soldered in across the pins. Since it kind of hovers over a ground plane, I decided to add some heat shrink sleeving on the wire that is not connected to ground. In hindsight, it would have been better to solder the shunt on the other side where there is no ground plane that could cause a short if the resistor was pushed down accidentally. And retesting rise and fall times with a shunt reveals that the funny rise time bounce is gone, while fall still looks as it should. Time to measure this properly by having the signal span 10 divisions vertically and checking the fall time between 90% and 10% signal levels with the cursors. Less than 600 nanoseconds fall time, which is in specification, and doing the same on the rise time by adjusting the cursors, reveals less than 650 nanoseconds, which is also fine. I assume you are as curious as I what the actual oscillator looks like under the solid metal cover. The cover is designed so that a part can slide out if 7 screws are loosened. And there's the oscillator, with a huge variable capacitor connected to the front dial underneath. The thing that looks like a horizontal light bulb is a thermistor, which is used to stabilize the amplitude. I tested the capacitors and they were all fine, and given the prices for new axial ones, I decided not to replace them. I took the opportunity to label the holes leading to trim pots and capacitors of the oscillator. This should have been done by the factory in my opinion, or at least the manual should contain a view where the holes are labeled. No such luck, of course. It turns out that closing the oscillator cover is a lot harder than opening. This is because I need to ensure that the washers are all in the right place before sliding the cover in and tightening the screws. Lots of fun keeping all the washers on 7 screws on 2 different sides aligned. The manual wants you to use the oscillator adjustments to align the frequency with the frequency dial markings for different ranges. The markings are roughly correct, and even with the best alignment, it will never be exact. Normally I use a frequency counter or a multimeter in Hertz mode anyway if I need the exact frequency of an analog generator, so I'm not too bothered with the accuracy of the dial. But I did add a substitute for the missing indicator mark by supplying my own on a little adhesive paper. In any case, before expecting any frequency or amplitude consistency from the J3, you better let it warm up a while, and depending on how important a constant frequency or amplitude is, that while may stretch to 3 or 4 hours. I'm beginning to understand why this unit was probably never turned off. To be fair, the frequency is actually fairly constant, just a bit more than 1 Hz over all that time, or 0.1%. Over the same time, the amplitude dropped by about 6%. While we're at it, I tested the flatness of the generator starting with a balanced output. The output level was set to 10 volts RMS. The picture here is probably a bit misleading. The variation over the whole range is just 0.15 decibels. It is maybe more obvious when I add the traces for using the -20 dB attenuator in red and the -40 dB attenuator in yellow. The low Z output has just half the variation of the balanced one. To put that into context, I changed the vertical scale to cover 3 dB on the lower graph. Pretty constant, I would say. As with the other graphs, I used my Agilent 34401A for the measurement of the low distortion output on the rear, expecting a similar picture as before. To my surprise, this was not the case, as you see here. Quite a significant drop starting slightly above 10 kHz. How could that be, since the same oscillator is feeding the other 2 outputs with no problems? Well, it's because the problem is with the 34401A, or more specifically, it's because of the high impedance of the low distortion output of the J3 and the 34401A AC input impedance. The 34401A in AC mode looks like a 1 mega resistor in parallel with a 100 picofarad capacitor. That capacitor makes the input impedance frequency dependent, and at high frequencies the 1 meg part can be neglected as the capacitive reactance dominates. The frequency doesn't even need to be very high. If the frequency is 10 kHz, the reactance is 160 kiloohms, and at 100 kHz it's just 16K. That is basically creating a voltage divider that will cause just 76% of the actual AC voltage to be measured. In reality, it's actually worse, as the capacitance of the connection cable adds to the 100 picofarad. The reason why this normally does not cause problems, at least in the range up to 100 kHz, is that the generator outputs have usually a much lower impedance. Even the 600 ohm of the balanced output still leaves more than 96% of the signal at that frequency. This, by the way, is not a problem just for the 3441A. I tested all my other multimeters and none fared any better. I retested the low distortion output using the scope with a proper scope probe having 10 meg and 17 picofarad on the input and therefore an impedance of nearly 100k at 100 kHz, and it was fine, of course. Some other observations that may be interesting. The speed of the oscillator amplitude regulation depends on the frequency. As an extreme example, if I switch from 1 volt RMS at 1 kHz to 10 Hz, you see that the amplitude bounces around for a long time before it settles back to 1 volt. I connected the TM3B because its big analog meter makes that easier to see. Even a change from 10 Hz to 20 Hz causes a little upset and several seconds before the amplitude is back to normal. This kind of bounce is really only noticeable in the 10 and 100 Hz ranges, and as you see here in the 100 Hz range it settles already much faster. Just something you have to remember when using these low frequencies. And with the TM3B connected to the square wave output, it is clear that the square wave is basically immune to the sine wave bounce. Out of curiosity, I checked the ripple on the primary smoothing cap C166. Which at roughly 45 volts DC was about 190 millivolts RMS with no load and increasing to 430 millivolts at full load. Since I had a 2000 microfarad cap of matching voltage rating and diameter, I decided to replace it, just in case. The schematic shows that the negative pole of the C166 is actually connected via a 1 ohm resistor R170 to ground, yet it is mounted in a metal clamp screwed directly to the housing. For this reason I decided to wrap the lower part of the new capacitor in a couple of layers of Kapton tapes for extra isolation, before mounting and reconnecting it. That reduced the ripple significantly to 90 millivolts idle and about 140 millivolts full load, but to be honest, this is mainly due to the new cap being 2000 microfarad while the old one was just 1000 microfarad. Because, as I had already confirmed while still in circuit, this old cap is fine, 1015 microfarad and 0.13 ohms ESR. And to get a second opinion, my recently repaired Vainker B424 component tester measuring with 100 Hz sine wave confirms this with 987 microfarad and about 0.1 ohm ESR. I tried to find date codes to establish the age of my J3. Well, the capacitors seem to be all made by Philips, and this one has an A1, which I believe would make it most likely January 1970. Other caps are marked with B, which would be 1971, and a small one here with C, or 1972. I think the early to mid 1970s sounds about right. Lastly, remember the handwritten note that the J3 can't sustain a full output voltage below 50 Hz? That is not the case for my J3, which supplies the 30 volts at 10 Hz with no problems. If I load the balanced output with a 600 ohm resistor, the voltage drops by half to 15 volts, which is exactly what it should do, since the impedance is also 600 ohm. The output impedance and my load resistor form a voltage divider with identical resistance values, so the voltage is divided by 2. A similar story with a low Z output. No problem supplying the full 3 volts at 10 Hz with no load. Adding a 5 ohm load and the voltage drops to 2.5 volts. Since the low Z output has 1 ohm output impedance, we now have a voltage divider with 1 ohm and 5 ohm, so the dividing ratio is 5 over 5 plus 1 or 0.83. The 3 volts coming from the generator times 0.83 is 2.5, which is exactly what we are seeing. Of course, there's a small deviation because of the tolerance of the 5 ohm power resistor. And that's it for this video. The J3 and J3B are for sure vintage, but still very nice bits of kit. Definitely worth maintaining and keeping around in my opinion. Let me know what you think in the comments. If you like my videos, don't forget to like and subscribe and help growing this channel. And consider becoming a Patreon. the links in the description. Thanks for watching.